of storage performance and flexibility for HPC and cloud data centers with, and now this title, I have to read it from my card, with the Senior VP and General Manager of the SSD and Cloud Software Business Units at Toshiba Memory America. Please welcome Mr. Steve Fingerhut.
Thank you very much. All right, thank you. Thank you to the CloudFest organizers for inviting me here and letting me present. And thank you all for attending. I want to talk to you about ride sharing your data center. So if you are managing your infrastructure, you are something like Uber, right? If you're Uber, you want your cars busy all the time. If you're managing your infrastructure, you want those servers and resources that you paid millions of dollars for doing productive work as much as possible. So let's see, there was a clicker. Very good. So we're going to talk about how NVMe-oF is really an enabler of a radical new efficiency in using your resources. So we're going to take an example of a real-life customer that we've been working with. They're a very popular e-commerce site. Most of us have probably used their services on many occasions. And for this example, they have two major teams. They have their online marketplace team, which has been the primary deliverer of the actual service to their customers, and then there is a new machine learning team. So they're trying to analyze their images, their past transactions, and come up with better shopping suggestions and recommendations. And of course, the online marketplace team, they have a very large data center at their disposal, and it's 100% utilized only a few days a year. So the busiest days, like Black Friday or Christmas, are the most busy. And then, of course, the machine learning team, the machine learning can benefit from more runtime. So the more time it's running, it's getting smarter. Any available computer resource they would like to use to make their recommendations even better. So of course, we know that in a peak, if they're 100% utilized, they can't be 100% utilized all the time. So if you average it out over the year, they're more like 50% utilized for most of the year. So you have the machine learning team, they're fully utilized, they want to add more images, they want to come up with better recommendations, and they say they need more servers. They go to the CFO, they make the pitch for more servers, but the CFO asks the question, why do you need more servers when all of these other servers are not busy? You could use those. Isn't that what the cloud is all about? And of course you say, well, it's not that easy. So the question is, what's preventing you from making that type of flexible data center? And so what's wrong? And really the root cause of the issue is one of the great enablers of success of the cloud. So direct attached flash, people use this today. You take SATA SSDs, you put them in a 2U server, you have your hard drives either in or outside of the server, but that gives you a very easy way to deploy flash. It's cheap, it's relatively fast, and that's just how the cloud has been built to date. But there's a couple problems, especially with the creation of containers and orchestration. It makes it even worse, but when you direct connect computer and your high performance expensive flash, those are hard linked, and you end up stranding the flash available and the performance available, and then that also means you're stranding your compute resources. So we'll go into more detail of what that means. So the question you're asking is, well, how much, if I'm going to do this direct attached model, the key question you have to ask is, how much flash should I put in each node? And to answer that question, I have a chart here. It'll be a few builds, but the bottom x-axis shows you the optimum SSD capacity, and that has grown, optimum SSD capacity per server. And that has grown over time as SSDs have become cheaper, and we've all grown used to using them. We're using them more and more. On the y-axis, we have the performance density, so IOPS per terabyte. And that's really most relevant as you think about these different capacities. The drives themselves don't get faster with more, the bigger they are. So a 1 terabyte drive and a 4 terabyte drive perform roughly the same. SATA maxes out, just the interface itself has a maximum of around 100,000 IOPS per second. NVMe is much faster. SATA stopped evolving in 2008, so it's not getting any faster. NVMe, of course, is based on PCIe, which is getting faster with every generation. So SATA taps out around 8 terabytes. NVMe, of course, will keep carrying forward for the future. The next, we'll look at applications. So applications, they're running logic, they're looking for data, they need that data at a certain rate. That's the IOPS per terabyte. So they're wanting that service available from the application, and that's a band because it's a range. Different applications have different requirements, but within a given application, it doesn't tend to vary much over time. And so one example from that e-commerce company we talked about, they basically size their NoSQL databases. It tends to max out at 100,000 IOPS per server. So those are doing complex transactions, and that's been their findings. So we draw that line, and that establishes what the application actually needs. So if we look at a couple representative applications, you have, for example, NoSQL for ad serving. That's going to be a pretty high-performing application, and you don't need much flash per server to make that an optimal configuration. If you look at machine learning, it's a little bit less intensive. It's looking for more data for every transaction it's running, so a little bit more in the middle. And then if you look at something like user profiles based on NoSQL, pretty much as much flash as you can put in, you're not going to use all of the compute and memory resources. So basically, if you're above that line, that blue line of what your application needs, you've put more flash in your server than you need, and you've stranded that flash capacity. And if you're below the line, that means you have more flash than you need, but not enough compute resources. So it's a little bit complex, but basically this shows applications will vary, and picking the perfect server configuration is pretty much impossible. All right, so we'll expand on this a little bit. We'll show how these different workloads vary. So if you look at something that's stateless, web server, for example, it does one, it gets data, it acts on it, it delivers a response. It doesn't need to save the information from session to session. And there you can see it needs a lot of CPU, but a little bit of SSD for a given application. Stateful are applications that keep that information and need to remember the state of the information from session to session, so things like ad serving or user profiles, and those can vary on their CPU requirements and their SSD requirements. And if you look at something like a batch job, machine learning that we talked about, or more commonly Hadoop, it's going to have a lot of CPU requirements and relatively mid to low SSD requirements. So once again, trying to configure this even on day one is you can do it manually. Day two, it's going to be out of date. So it's very tough to optimize these node configurations. So here we will look at, let's take those workloads, let's put them in an example rack. This could be multiple racks, data center level, and then we're going to look at how that plays out over time. So this is a snapshot in time. We're going to look here. This is over a 3-year period. So you can see the y-axis is the number of compute nodes. And so you can see batch jobs, the stateful jobs, the stateless jobs all have a certain requirement of the number of servers. And the e-commerce company I talked about that we've worked with, they basically build up for their peak periods over the year. So that's why you see they're building up for Black Friday. You can't wheel in the servers the day before Black Friday and expect everything to work. You have to stage those over the year. So just built in, you have loss. So stateful jobs are linked to a certain set of servers. The stateless jobs are linked to a certain set of servers, and of course the batch jobs are as well. You can't mix between them, so within each group there's loss. And then there's something we call bin packing loss. So even within those, you've done a pretty good job of picking the servers. Maybe you have a compute-heavy standard configuration, a memory-heavy server configuration, and a storage-heavy. And you've done your best, but that big gray bin packing loss is within each one of those, you have excess memory, excess CPU, or excess storage, and that's all lost resources that you could be taking advantage of. So the challenges here, if you look, okay, we've put some standard configurations in place, but in this example, we now have stranded flash in those top servers, which is lost money, and then of course you have stranded compute. Those applications are not maximizing the use of their expensive CPUs. So let's talk about then disaggregation. So we're here to talk to you, the main point of my presentation today is about NVMe over fabrics. It's a way to take that high-performing flash and disaggregate it. So let's say you've taken that, you've put it into a central storage server. Now you can see those drives, there's fewer drives, but they're packed very tightly. So that's going to give you an immediate savings. But what's not so obvious is you will actually, so first you'll have that optimal storage savings, which eliminates the flash, but then you can actually manually place the jobs in better, a more optimal configuration, and just by the act of disaggregating your flash, you can get a significant savings in the number of servers that you have to deploy for the same workload. But you'll see you still have a lot of stranded capacity, and you're not really an agile operation. You're a little bit more efficient, but you're not agile. So let's keep going with that. So you've not only you've spent too much money, but now you can't adjust. Perhaps you've done this disaggregation, you're buying fewer servers, but you can't adjust to changing workloads, changing demands. And that costs you agility, which could cost your company revenue. All right, so let's talk about, there's been a lot of discussion earlier today about the value of containers and when you orchestrate those. So let's look here at what happens. So we've got, now we've done this disaggregation. We've got containers running on all of our workloads in container environments, and those are orchestrated. So right away you can see we're using all of the CPU resources on the chart on the right. And we can now borrow those resources as needed depending on demand. So you see the green arrow goes down, the number of servers goes down. You'll also see those peaks for Black Friday and Christmas, they're now inverted. And what that means is we are now borrowing resources from the batch jobs to handle our peaks. And so we're slowing those down on the peak days, still getting it done, just in off-peak periods when they're not as time critical. And now I think there's going to be a very fancy animation. So you watch this. This shows it over time, and you can see the CPUs themselves adjusting to the period. So then the machine learning or batch jobs slow down. They take up less of the CPU, give more to the stateful and stateless applications to scale and meet the specific demands of the day. But this is only possible if any application can run on any node, which is essentially the container and orchestration environment, but also if you were to do containers and orchestration, but still with direct attached flash, then your data is going to keep you limited. You're not going to be able to access that data from any node, and you will not be able to get these types of resource improvements. All right, so let's look at what flash-enabled agility looks like in your data center. So Google gave a presentation recently where they have modeled this very carefully, and they saw anywhere from 30 to 60% compute node savings on pretty much any workload they could define. So ran it through the same model and got a significant savings. So that obviously saves you cost. You have fewer server nodes to manage, and it allows you to rapidly adjust to changing business conditions. All right, so let's go back to our problems, and what we see is that shared accelerated storage is really a key part of the solution. Let's talk about what that gives you then. So we have our first problem, we've been buying too much flash and leaving that performance underutilized. So the first bit is you buy fewer SSDs, so your capital expenditures go down. Second problem was compute. Now you're buying fewer servers. Not only is your capital expenditures down, but your cost to administer those is also down. And then finally, you have the ability to actually respond more quickly to changing business environments and changing workloads, and you can increase your revenue as a result. So then the question is, this sounds great. So why haven't we been doing this? Why have we been stuck in the direct attached world? And really, there's been some key pieces missing. So the first, high bandwidth, low latency networks are now becoming common. More than half of servers are deployed with 40 gig or higher networks now. So this is all very standard and becoming more so by the day. You have these mature orchestration frameworks. Kubernetes, OpenStack are available and make all this possible. Companies like Toshiba are building very fast, very large NVMe SSDs, and the pricing is coming down rapidly and more closer to what SATA has been. And then, of course, the NVMe over Fabrics protocol. So this allows very low latency access to a flash tier, unlike anything that's been available before. But you can see there's a missing puzzle piece, and that is Toshiba is now, or soon will be offering shared accelerated storage software. So this will be software that turns your server into a flash storage node that can be available to any of your applications. All right, so let's take a look at what that looks like. You have your example rack here. You've now got your NVMe SSDs and a storage server below. And the Toshiba software is now managing that node. The first thing it does is it virtualizes and abstracts all the SSDs. So you can manage those as a pool, presents a namespace to your services, however they want to consume them, and then there's a management engine that presents a RESTful API for your third-party orchestration framework, or we've also talked to a lot of companies who have built their own orchestration frameworks, and we have the RESTful API to keep to link into those. If we think about the benefits, the first thing you want, of course, is for it to be fast. And we have end-to-end across the network, we've measured less than 20 microseconds latency adders. So take your fastest NVMe SSD, put that in a server versus in this network-attached device or network-attached server, and it will be less than 20 microseconds. So to put that in perspective, a typical SATA SSD running in a server averages around 200 microsecond latency. NVMe drive will be around 90 microseconds. So we're talking about a very small increase, and you will be much better performance than if you're using SATA. And then, of course, millions of IOPS. This is essentially saturating the network interface, and it's as many network interfaces as you want to add as how fast it will go. All right, flexible, thousands of namespaces, hundreds of terabytes. This is just one example, but as pretty much as many as 1, 2, 3 multiple racks can handle. Future-proof, we're going to be doing all the integration with the popular frameworks, with all the key software that you're using day to day. We keep that up to date. You don't have to worry about what's coming down the road. All right. Okay. And then optimized. All right, my builds are acting funny here. So optimized, you're not stranding any flash and you're able to be completely elastic to whatever your demands are. All right, and I haven't even talked about Toshiba at all. Just to do a quick introduction, we invented flash memory, and we're the first to ship 64-layer 3D NAND, the most cutting-edge technology. We'll be launching our 96-layer based SSDs later this year. So best cost structure, highest performance, highest endurance in the industry. We operate the world's largest flash fab. When you want your supply, you want it fast. Toshiba has it. We're a leader in this space. I need better latency on my clicker. It's not working so well. And decades of storage experience. We are a major supplier to 5 of the top server vendors and 5 of the top 5 and 5 of the top 5 storage vendors. So we are built into every major system vendor that you're buying from today. And what they're buying from us is a broad range of SSDs, so NVMe, SAS, and SATA. All right, and please come by our booth. And there you can see a demo of the software, and you can also look at the portfolio of SSDs. So thank you very much.
Thank you so much, Steve, for Toshiba